Okay, we got a fun section for you. We're going to cover section 7.1, and I will get up next section early tomorrow morning, as well as a study guide for the test. Anyway, we will begin. So, there's three sections in chapter 7, and just this first lecture here is just going to cover oxygen binding to myoglobin and hemoglobin. And you'll find out that that is plenty enough to cover in one lecture. So we're going to, this chapter focuses on proteins that have function. And so in the first one, we're going to look at O2 binding to myoglobin and hemoglobin. And then the next two portions we'll put together muscle contraction and antibodies. So we got a picture of a very cute fish down here known as an ice fish, and it doesn't use hemoglobin to carry oxygen. It lives in very cold water. It's not very active, and oxygen is more soluble in cold water. And so it can transport enough oxygen in its plasma without binding to a specific protein. Well, we're a little bit more active. We live at a higher temperature, and so we need some oxygen carriers. And so we're going to talk about myoglobin and hemoglobin and how they are used to carry oxygen. A little background to myoglobin is it was the first protein to have its complete structure identified. And it was finished in 1959. So there's a really interesting box that you should read on this process. It took them a long time. In fact, Max Perutz essentially spent his entire life dealing with myoglobin and hemoglobin. And so the model below is derived from their X-ray data. And this is interesting. It's got a bunch of alpha helices and some turns, and it's got what's known as a prosthetic or a heme group. We'll get a better picture of that in just a second. So when they came up with the structure, they named each helice starting from A to F, and then they indicated the regions as they transitioned from one helice to the other as the AB. So those terms we'll see again, especially the F helix. So myoglobin is a monomeric oxygen binding protein. So you can see its tertiary structure here. It's made up of alpha helices that have turns, and then again it has this heme group that then has an iron in the middle. And the heme is held in place by hydrophobic interactions. So it's non-covalent, but hydrophobic interactions stabilize its position there. And then the iron is actually coordinated by a histidine residue coming from the protein there. And so myoglobin is an example of a highly compact globular protein with mainly helical proteins. So this would be classified as an alpha helical protein. And so you can see here kind of a structure around where the heme is, space filling model. So it looks kind of open here, but actually where the oxygen binds is actually somewhat hidden and protected by the protein. Here's a little diagram. Again, we'll see heme in just a second, but here's the heme. This is where the oxygen binds. And again, it's surrounded by these hydrophobic residues, and it actually has coordination from histidine residue, and then it also has another histidine residue up above it, which we'll refer to as the distal histidine. And so let's take a little bit closer look at what a heme group is. So a heme group is a porphyrin ring that actually has an incorporated iron into it. Now, the iron that's active in myoglobin and hemoglobin is actually an iron 2 species, but if you expose a heme group, a free heme group, to oxygen, that iron will get oxidized to iron 3. That doesn't happen very fast or frequently within myoglobin and hemoglobin, and that is due to this protection from the protein. So we've got this histidine residue. This is where the oxygen is going to bind. But remember from the previous picture, we actually had some hydrophobic residues that helped protect the iron from getting oxidized. Now there is a change when this porphyrin ring actually binds the oxygen. In fact, this is what's referred to as kind of a taunt structure. It's bent out of the plane a little bit. And when you bind the oxygen, the porphyrin ring will actually relax and become actually more planar there. And so these are referred to when we talk about hemoglobin as the tense state. Oh my goodness, sorry. Tongue-tied, tense state and the relaxed state. So the relaxed just meaning the porphyrin ring is more planar, where here it's actually deflected out of the plane. It's kind of in a tense structure there. And so this changes when the iron binds. What's really interesting is actually the diameter of the iron actually changes due to d orbital splitting when the oxygen binds. It's not something that we really talk about here, but if you go and look at or take an inorganic class, you'll talk about this crystal ligand field splitting theory. And the iron radius will actually change as the oxygen binds. It becomes a little bit smaller and fits more nicely, more snugly into that heme group there. So oxygen will bind heme. It will bind it within a protein and outside of a protein. And you can actually change its redox. And so you can actually see those changes in this heme group. It's a chromophore in the UV-Vis spectrum. And so when the heme group doesn't have an oxygen, it has a maximum peak right around 560, which is more in kind of the blue region, I believe. And then in oxyhemoglobin, you actually see that you get these two other peaks here. So if you just have iron 2 heme, it ends up being a dark purplish. When the oxygen binds, it becomes a brighter red. If you leave the heme out or you expose blood to a lot of oxygen, it will eventually get oxidized to the iron 3 and it turns kind of a rusty brownish. And so that's where you get the characteristic color of dried blood, is when you get the iron 3 in there. Now to this heme, other molecules combine, carbon monoxide, nitrous oxide, and hydrogen sulfide. And they tend to bind with much higher affinity than O2. And if you don't know, carbon monoxide is very toxic. And hydrogen sulfide has about the same toxicity as cyanide. Cyanide will also bind to heme groups as well. And when you start binding to your heme groups and oxygen can't bind, that leads to problems. So let's talk briefly about myoglobin. And it will bind oxygen and it helps facilitate the diffusion of oxygen. So oxygen is really not very soluble in water, especially at higher temperatures. Water doesn't dissolve gases at very high concentrations. But myoglobin does increase the effective solubility of O2 in muscle tissue, and we'll talk about that specifically. And aquatic mammals actually have around 10-fold higher myoglobin concentration than terrestrial mammals. And so aquatic mammals actually use myoglobin for oxygen storage. So we've got a seal here. I don't know if you remember a couple years ago, there was a big issue of teenage seals snorting ills. So that's an eel that stuck up the seal's nose. I believe this was in Hawaii, and this isn't just a one-off occurrence. They found several cases. They don't know if the eel just swam up his nose or these kids were like looking for a high, like kids snorting Smarties. So the purpose of myoglobin, it does help oxygen diffuse, but you can knock out the myoglobin gene in mice. You notice a couple things that the mice will tend to have more red blood cells, and they actually have increased capillary densities in their muscles, meaning that they need greater density of the capillaries to deliver oxygen there. And if the mouse lived, it seemed to be fairly functional, but many died in utero from cardiovascular defects. So there are other oxygen carrying species. We'll talk about those before we jump in depth into myoglobin. So there are other types of oxygen storing proteins and groups. One that's interesting down there, and I'll give the bonus right away, is the hemocyanin that's found in mollusks and arthropods. So these are horseshoe crabs here. And if you didn't know, there is big business in milking the blood out of horseshoe crabs. Their blood tends to have a rich blue color, and that's because it's actually a copper atom, well, actually two copper atoms that are coordinated by histidine that bind the oxygen. And so you can see here them milking the blood out of these horseshoe crabs. So the bonus question is, what do they do with the horseshoe crab blood? Why are we milking the horseshoe crabs? What's the purpose of that? Lots of interesting information out there. That should be an interesting and easy bonus point for you. So again, arthropods, mollusks actually use a different type of protein that instead of iron has some copper atoms to transport oxygen throughout their system. And I guess I really haven't answered, hopefully you read in there why we need oxygen to be transported throughout an organism. The diffusion of oxygen, like I mentioned, just in solution, the concentration's low, but the diffusion through large animals would be slow too. And we actually use quite a bit of oxygen. So we actually need a way to get large amounts of oxygen within the organism. So annelids, they use this erythrocuronin. It's a giant free-floating protein, so it's not encased in a membrane. It's got many globin domains, and it is how earthworms carry oxygen through themselves. They tend to be really large. You don't want a lot of small proteins in there because that would dramatically increase the osmotic pressure. So they tend to be huge and bind lots of oxygen. Okay, so let's get back into the hemoglobin and myoglobin. And how does it bind oxygen? So like I mentioned, you've got this heme group, and you got a proximal histidine residue that's in close proximity. And then that allows one free coordination site for the oxygen to bind. And so you can see over here is myoglobin, and it is a single protein. And here is the distal histidine. And so the oxygen can come in and bind there. So binding to myoglobin is actually simple. Binding to hemoglobin, you've actually got 4 heme sites and causes the protein to undergo conformation changes. And so it's complex. So we're first going to look at myoglobin because the binding we can model simply, and then we'll look at hemoglobin that's actually more complex. Just a little side note about the binding of carbon monoxide. If you have a free heme group, the carbon monoxide actually has a lone pair that coordinates very strongly with iron. In fact, it binds 20,000 times better than oxygen to a free heme. But within the protein pocket, myoglobin and hemoglobin, it only binds 250 times better. Still better than oxygen, but you know, a couple orders of magnitude less so. There's a couple reasons for that, and one of them is this distal histidine that actually covers this top site and helps orient oxygen that comes in. But when carbon monoxide tries to bind, it actually has some steric interaction with that histidine. So the binding pocket for oxygen is set up optimally, and there's some sterics there that prevent the carbon monoxide from binding efficiently. But since it binds so tightly, and once it wiggles its way in there, it pretty much sticks. If you get carbon monoxide poisoning, it takes a while to get it out of your blood. And the reason it's toxic is it replaces the binding sites for oxygen, really hard to come off, and then you can't deliver oxygen to your cells. So you can end up dying from carbon monoxide poisoning. So, like I said, the binding of oxygen to myoglobin is simple because you just have one subunit, but when you bind to hemoglobin, there's lots of changes, and we'll look at these in greater detail. But the channel in between the subunits gets smaller, and you get reorganization of a lot of these side chains. If you notice, this side chain's kind of tucked in between these two valines, and up here it actually moves significantly. So some of the movements are up to 6 angstroms. So there's a lot going on when you bind to hemoglobin, so we need to talk about that a little bit more in depth later. But let's come up with a model. So we've got some math here. Now, if we look at this top equation, we're just going to generalize it, a little bit different than the book, but we've got a macromolecule and an A. We're just going to refer to that as the agent that's going to bind to the macromolecule. And then you get the complex, the macromolecule and the agent there. Now, if you set up an equilibrium, you would have products over reactants. And so you just have Ma over the concentration of M and the concentration of A. But you notice, actually, we don't have the equilibrium expression. We have Kd, which is the dissociation constant, which is actually looking at the reverse. So really what we want to find out when you're binding to proteins is how strong does something bind? So if you have a very small, dissociation constant, that means that you bind very tightly. You don't like to dissociate. And so we can set up this dissociation constant. So it's different than an equilibrium constant. It is essentially just the inverse, the reverse. And we can rearrange that. So all we did was put Kd on the bottom, and then we just have the concentration of our molecule of interest being bound to the ligand of interest. Now, another equation that we need to work out is the fractional saturation of the macromolecule. So if we have our macromolecule and it's bound to A, how much of our macromolecule is bound? Well, we can figure that out by taking the amount unbound plus the amount bound. That would give us a total. And then we simply take the amount that is bound. So you take the amount bound by the total molecules, and that's why you have to sum those two together. And that is going to give you a fraction. So not really a percent, because we're not timesing by 100, but a fraction. And that will give us our fractional saturation. Essentially, how much of our molecule as a fraction is bound with the ligand. And so we can actually substitute these two equations together. And you can do the math yourself. You end up with this really ugly mess right here when you put this into that spot and this into that spot. And that is how you get this equation there. And then what you can simply do is factor out the m's. Those will all cancel out. Notice here that these kd's on this term will cancel out, but you'll end up with a kd here. The whole point is we end up with a fractional saturation that is related to the substrate and the dissociation constant. So now we're essentially dealing with constants and the concentration of our substrate. We don't have to worry about the concentration of the protein there. So it just makes it a little bit easier because we don't have to measure two concentrations here. We just need to know the dissociation constant and how much of the molecule we're putting in. And if you just plot this, you end up with a rectangular hyperbola. And so what that means as our fractional, well, actually, let's read it this way. As we increase our A, our fractional saturation increases, and eventually this would approach 1 there. So the fractional saturation depends only on how much of A we have and the dissociation constant, essentially the affinity that this protein has for molecule A. And so this is used in any simple binding in biochemistry where a ligand interacts independently with the binding site. So such as ligands binding to proteins, substrates binding to enzymes, a molecule binding to a cell surface. So this is kind of the simple model right here. And this is what happens in myoglobin. Okay, so again, this is a regular hyperbola. And that's the exact same slide. If you're wondering why that's there, the Department of Redundancy Department approved that inclusion. So we can look at this model here. And again, what we've done is we're looking at the fractional saturation and the concentration of A. And so that just means the variable would be the dissociation constant. So as we increase our dissociation constant, you can see that we actually change the curve here. Okay, and so if we go over and look at these graphs right here, one of the values that we'll be interested in is our half saturation. So when are things half saturated? Kind of arbitrary, but that lets you know that half your molecules are saturated and half of your molecules are unsaturated. And what's interesting is you can plot here and figure out your KD from these graphs here. And so at that point there, this is a lot like the Henderson-Hasselbalch, when your A minus equals your HA, then your pKa equals your pH. So kind of similar. So when you're half saturated, that point on that graph gives you the KD. Down here, you notice that we have very small concentrations, and I'm half saturating. Here, I have to have a lot higher concentration to get half saturation. So what we'd say is that this has less affinity for the group A right here. So essentially we're decreasing the affinity as we go this way. It's easier to release or harder to bind as we move in that direction there. Okay, but we want a specific example. We're going to talk about myoglobin, and when we look at myoglobin, what we want to do is look at the fractional amount of myoglobin that's bound to oxygen, and it will be easier to deal with pressures of O2 than actual concentrations of O2. And again, we'll have the KD. And like I mentioned before, sometimes the KD is referred to as the P50. The pressure of the O2 at which myoglobin is half saturated. So if I look right here, this would be the pressure when myoglobin's half saturated, which we showed you earlier was the KD. So I can actually substitute this KD out for what we refer to as P50 right there. So I'll write that P50 is equal to KD, the dissociation constant. So for myoglobin, the P50 is 2.8 torrs. meaning you don't need very much concentration of oxygen to half saturate. That means that myoglobin's got a pretty strong binding affinity for oxygen. It doesn't really like to let it go. So if we look, the pressure of oxygen in arterial blood, so essentially right when you're coming out of the lungs, is about 100 torr. In venous blood, after you've gone through and you've delivered, is about 30 torr. Now, to be half saturated, I need to get myoglobin down to 2.8. So really what we're looking at is at 30 torr, even in our body at the lowest pressure that we get, myoglobin is mostly saturated with oxygen. So myoglobin really is a bad oxygen delivery agent. It grabs onto it and it doesn't really want to let it go. You'd have to get to very, very low concentrations of oxygen before myoglobin would start to let go. It does play a role though, we'll get to that. So in fact, what we wanted to look at is for effective transport affinity, you must vary the PO. You must vary the PO. So again, this is kind of like myoglobin here that has a high affinity state. And so in the lungs, it's going to bind lots of oxygen. And in the tissues where the oxygen's low and we need to deliver, there's not going to be much delivery. It's not going to let it go. Well, you could have a low affinity state. The problem is you're just not going to pick up much here. And then when you go to deliver, you will release some, but the amount that you're releasing is fairly small. So what would be awesome is if you could pick up a lot, and then when you enter the low pressure, you're going to deliver a large amount. So you don't want this hyperbola. You'd actually kind of want this sigmoidal curve right here. And we'll find out that this sigmoidal curve corresponds to cooperative binding, meaning that we're going to have more than one site for the oxygen to bind. And as I bind one oxygen, it's going to be easier to bind the next one. Okay, so hemoglobin is more sensitive to small differences in oxygen. So hemoglobin will bind oxygen in the lungs when the concentration or the pressure of the O2 is high, and it will release a significant amount in tissues when the PO2 is low. Myoglobin will bind oxygen in the lungs and it keeps it bound in the tissues. But myoglobin really isn't used for transportation. Like we said, it's actually found in muscles. So we'll talk about its role there. We're just comparing and contrasting right now. So hopefully you get the take-home message that myoglobin is not a good oxygen delivery agent. So let's move on to hemoglobin and figure out what we need to do to make a good delivery agent for oxygen. So as I mentioned, there are different states of that heme group. And so they actually refer to these states not just as a heme, but the overall protein. So it's got two stable conformations that have different affinities for oxygen. So you got the tense state, more interactions, it's more stable, and it doesn't have it's got a lower affinity for oxygen. So this is the conformation when you really don't have oxygen bound. It's kind of interesting that this doesn't have a high affinity when there's no oxygen around. And then you get the relaxed state. So you got fewer interactions, it tends to be more flexible. In fact, this R state has a higher affinity for oxygen. Well, if I only had one binding site, this doesn't make sense right here. This only makes sense if I got more than one binding site. So what this means is, well, when there's no oxygen bound, I don't have a affinity for any oxygen. And then the R state, what this means is if I have multiple sites, when one oxygen binds, I get greater affinity for a second oxygen and maybe even a third. So what happens is it's hard to get the first O2 on, but it does trigger a conformational change from the tense to the relaxed state or the T state to the R state. Well, now that I'm in the R state, it's going to be easier to bind that second oxygen and even the third oxygen. So oxygen binding in one subunit actually helps another subunit bind an oxygen, and then that will help an additional subunit bind oxygen. And this only takes microseconds to occur. So I just want to talk a little bit more about this cooperativity. And so this is just a generalization, but structural stability through a protein is not uniform. So we've got a hypothetical protein here, and it's got those flexible red binding sites, and they're just kind of flopping around, and the binding sites there in the blue. And so then what you see is once we get binding of one ligand here, we actually get less flexibility here. And as we get less flexibility here, that will actually make it easier for the next one to bind. So the conformation changes, and it allows the next ligand to bind more easily. And that's referred to as positive cooperativity. And you can have negative cooperativity where one ligand binds and then it's harder to bind the next ligand. But we want to focus on oxygen. The ligand that we're binding is oxygen. We're binding it to a histidine residue. And as we mentioned, hemoglobin has 4 subunits. It's got 2 alpha subunits and 2 beta subunits. The alpha subunits you can see here are in gray, the beta subunits are in blue, and the gray units are identical and the blue units are identical. So we can see in the T state, remember this is when oxygen's not bound, that each heme is about 0.6 of an angstrom out of plane. So I talked about that. There's a little pucker of the heme there. So as the oxygen binds, it actually changes the heme's electronic state, and it actually shortens that nitrogen, the porphyrin iron bond, and it actually brings this histidine in closer. So you tug on that histidine because the iron starts to sink into the middle of that ring. And as you do that, you actually pull the it's this coil right here, but you actually pull this coil in towards that heme group there. And that causes conformational changes. You can see this big gap right here. And as I start to bind oxygen, this coil this alpha helix has been pulled in, and that starts to collapse this interior there. So if it's this F helix that when you bind oxygen is dragged towards the heme group, and you actually get fairly large changes. Just take a second and look at the difference between those two and see if you can identify other differences between those two structures there. And what's interesting is just that binding here actually has effect on all the neighboring groups there. So here's a little bit closer picture of the groups that actually change. So at the interface between the alpha subunit and the beta subunit, as you bind oxygen, this helix actually this group will actually move up the helix. So you notice that there's a histidine here, and as it binds oxygen, that histidine actually moves up between these 2 threonine residues right there. So this is the T state, deoxy. So this is a little picture in your book, and you can kind of see that these bumps of these hydrophobic residues and this histidine kind of fits into that. And then as it binds, you actually get kind of I'll refer to it as a register shift. You actually shift these bumps up to new grooves there. And so you actually get a big change in that interior cavity of the hemoglobin as you do this. Let me, if I can, get to the next slide and actually show you what's happening to the F helix, which has that histidine is complexed with that iron right there. Again, you can see kind of the pucker in the porphyrin ring, and this is the T state without the oxygen. When the oxygen binds, the iron actually gets smaller, fits in more nicely into the porphyrin ring. This goes flat, and that drags that histidine closer, and you'll drag this F helix. And so that is thought to be what accomplishes a lot of the molecular motion on oxygen, simply changing this radius and dragging that proximal histidine in. Here's just another picture. This one's out of your book. And so you can see that the blue is the T state, again, the pucker in the porphyrin, and the F helix is further away. And as you bind oxygen, you go to this red or the relaxed state. The porphyrin's more planar, and that will drag this histidine. So everything in red is in the R state there. Okay, so there are a bunch of coordinated events when you bind oxygen. So these subunits are so tightly coupled that large tertiary structure changes in one subunit can't occur without quaternary structure. So just like any one person in this world is connected to other people, so your actions can't occur in a vacuum. So changes in one subunit will change the conformation in adjacent subunits. And anyway, this is kind of what we've said before. The T state and the R state have different affinities for oxygen. The KD decreases as molecules of the protein shift from the T state to the R state. Okay, so let's look at some graphs and actually see what's happening here. So myoglobin, like we said, has this hyperbola graph when we look at the fractional saturation and essentially the pressure of oxygen, where hemoglobin actually has this sigmoidal curve. And I talked about that sigmoidal curve earlier as indicating that there's coordinated binding there. And this coordinated binding is very important. Like I said, myoglobin's not good at releasing oxygen, but with this sigmoidal curve here, we bind oxygen under high concentrations and tend to release it under low concentrations. And why this works is, well, if I bind one oxygen, then I'm likely to bind other oxygens. Down here, if I release one oxygen, now I'm more likely to release the other oxygens. So there's this delicate interplay between these subunits where myoglobin only has one binding site. So it's kind of all or nothing type of binding. Either the myoglobin's there or I get to a low enough pressure and the oxygen will dissociate kind of all at once. Okay, so if we go and actually write the KD and use the terms for hemoglobin, we need to add in some additional numbers. And just like when you're writing an equilibrium constant, you have to take into account the prefix or the stoichiometry there, and you raise it to the power. So remember, this isn't an equilibrium, we're doing the reverse. And so what we want is essentially the reactants over the products because we want the dissociation constant. And notice we now get this N term right there. And we can derive the equation for the YO2 like we did before. And notice when we do that, we also get this N term right there. So in this case here, we end up with an additional factor that we need to consider. So N is a non-integral parameter relating to the extent in which binding is cooperative. If N is 1, then that means that binding is non-cooperative, and we'd see a graph like we see for myoglobin. If N is anything other than 1, then you start to get some cooperativity. Now, in the case of hemoglobin, N is, if we look at the number of binding sites, N can equal 4. So in this equation here, if N equals the number of binding sites, so if N equaled 4 here, that's going to be kind of the max number that we get, then all ligand molecules bind at once. It's infinitely cooperative. meaning somehow those molecules, as they start to bind, they would all bind and have the same impact. Well, that's not true for hemoglobin because we know that it's hard to get the first one off. So the N for hemoglobin is around 3-ish. And so how can we actually figure this out? Well, we've got to do some maths. And so again, this is the equation that we derived before. The difference here is that we have to take into account the stoichiometry. So that's why we end up with these N's there. Well, let's make this into a form that is a little bit easier to deal with. And so what we're going to do is do some math, and we can rearrange and end up with this equation right here. Okay, so all we've done is rearranged it, and like we did in the earlier example. And if we actually take the log of both sides of this, we end up with something interesting. You may remember if you take the log of a fraction, that actually can be expanded into this form right here. So where the log of the top is subtract the log of the bottom. Now I'd expect you to derive this because it hurts my head as well, but I do know that this is now similar to y equals mx plus b. So this group right here is y. So if I plotted the fractional oxygen over 1 minus the fractional oxygen and plotted that against n on the log of PO2 minus n on the log of P50, which is also, remember that could also equal the dissociation constant. Okay, if I do that, I can end up with this form of y equals mx plus b, where y equals, like I said, this. So that's what we're plotting on the y-axis. X equals this. Notice we're plotting that on the x-axis. And then the slope of the line is n. Okay, now you notice that this is a sigmoidal curve when we plot it on this log-log plot. And so actually, if we took this plot right here, or sorry, this slope, that would be the slope essentially when you've got no cooperativity, okay, or when the first oxygen binds. But once the first oxygen binds, then what we do is we get this slope. So we want to determine the slope here. And the slope of this line will actually give us the cooperativity of this enzyme here. This is known as the Hill equation and the Hill plot. And so you know that hemoglobin here actually has a slope of 3. So it has a cooperativity of 3. So it's not perfectly cooperative. If it was, then that number would be 4. And so essentially what that means is oxygen's not going to bind all 4 oxygens. There's always going to be some hemoglobin in there that don't have all 4 of their oxygens bound. Okay, so if we compare myoglobin Hill plot with hemoglobin's Hill plot, you can see that that myoglobin's plot crosses the YO2 line at around 2.8 torr, which we said was a really low concentration. So it's not able to really release much oxygens. But since hemoglobin is curved, this will also show us that the oxygen will be released at a higher partial oxygen pressure. Essentially, it's going to be held less tightly. Okay, so just comparing those two plots there. So the P50 for the initial binding is kind of here. So when hemoglobin is in the T state, what we can say is the affinity for oxygen is low. But the P50 for the last bound oxygen is close to saturation. So most of the hemoglobin molecules are already in the R state, and with a few of the remaining spots on separate hemoglobin molecules. So like I mentioned, the hemoglobin doesn't always get completely saturated there. Okay, so there's some other effects on the cooperativity of the O2 transport, and that is the Bohr effect. As I mentioned before, we want to talk about how hemoglobin and myoglobin work together in the body. And then there's an interesting molecule, 2,3-bisphosphoglycerate, that actually stabilizes the T state. So you should be able to predict what that does. If it stabilizes the T state, it actually has less affinity for oxygen. And actually, it will help facilitate the release of oxygen because it's going to stabilize the T state, the one that has less affinity for oxygen. So first of all, let's look at the Bohr effect. So there's ion interactions in the T state. And these ion pair interactions actually give groups higher pKa values. So we talked about this before, where you get microenvironments and the pKa can actually shift. So here we can look at the alpha chain, the N-terminus, and in the beta subunit, histidine 146. And so you can see those interactions down here in this diagram there. So in the R state, these pKa values decrease. And what happens is you bind oxygen, you're actually going to become, essentially hemoglobin becomes more acidic and actually releases 0.6 protons for each O2 that it binds. So it actually starts acting as an acid as you acts as an acid as you bind O2 and will release H+. So the reverse is true. So raising the pH, making it more basic, actually stimulates the hemoglobin to bind more O2. So what we could say is that, well, actually, let's look at this graph here. So at high pHs, you tend to release less oxygen, and at low pHs, you tend to release more oxygen. Okay, so we can see that here. Lower pH, lower affinity for O2. And higher pH, higher affinity for O2. So in tissues, when we use up oxygen, we're actually going to create CO2. And CO2 reacts with water to make carbonic acid. So deep in your tissues where you're losing lots of oxygen, you tend to be a little bit more acidic than in areas that are highly oxygenated. And that should make sense. As I'm using up the oxygen, I tend to get more acidic. And as I get more acidic, that actually causes the hemoglobin to favor the release of O2. It favors the T state and the release of O2. So that should start to make sense that if we can favor the T state, that means that we're in a more stable state without oxygen. So we're releasing oxygen. If we stabilize the R state, then we are favoring the binding of oxygen. So again, reducing the pH favors the T state and the release of O2, or oxygen there. Okay, so in lungs, we have high oxygen concentrations, and that's going to drive the shift to the R state. That's going to favor the bound state and release of the acid from hemoglobin, because we want to get to a more basic condition which favors the R state so we can bind more O2. Increasing the H plus shifts the equilibrium towards the formation of CO2 from the H plus and the carbonic acid. So in the lungs, as we exhale CO2, that shifts the equilibrium towards CO2 formation. Oh, sorry, I'm not quite sure what that means. I do know that as you go to your lungs and you release, oh, I know what it is. As you go to your lungs and you release CO2, the carbonic acid is going to form into CO2. And so you're going to release more CO2. Essentially, this is Le Chatelier's principle. If we can get rid of the CO2 by exhaling it, then our body, the carbonic acid in our blood, is actually going to form even more CO2. So at the lung air interface, we release lots of CO2 because as the CO2 releases, the carbonic acid turns into more CO2, which escapes from our lungs. So we do have an enzyme in our tissues and lungs, carbonic anhydrase, that actually accelerates the interconversion of CO2 and bicarbonate. So deep in our tissues, we would take that CO2 that's in high concentration and make it into bicarbonate. In our lungs, we would take that bicarbonate and accelerate the production of CO2 so we could release that. Okay, this is known as the Bohr effect, the effect of pH on the uptake or the release of oxygen. I told you that we would talk about hemoglobin and its role, or sorry, myoglobin and its role in O2 transport. And so in our muscles, deep, far away from our lungs, we have myoglobin there. And it has a much higher affinity for oxygen. So as the blood is being transported and picks up oxygen and goes down near the muscles here, okay, it's going to release a little bit of oxygen. But if that oxygen didn't have anything to bind to, then that oxygen would just diffuse back and bind with the hemoglobin again. So we want to take advantage of essentially Le Chatelier's principle again. And what we want is something on this side that has a high affinity for oxygen. So as oxygens fall off here, it's going to bind them tighter. And as it binds them tighter, it's going to shift that equilibrium. So hemoglobin is going to release even more and more oxygen. And then the hemoglobin, or sorry, the myoglobin, you just need to get to a low enough pressure or to a high enough concentration of the myoglobin with oxygen that it will then release the O2 there. And this is in your muscles, so you've got CO2 in there that you're producing. That CO2 then goes out and is converted into carbonic acid. Remember, this makes it more acidic, which makes it even more likely that the hemoglobin is going to release the oxygen. So you're going to release the oxygen in close proximity to the muscles. You just want to make sure that that oxygen has something that has higher affinity for it. We're going to talk about that later with fetuses. They actually need a higher affinity for oxygen, else they wouldn't be able to pull the oxygen away from their mother. So there's two more points about the Bohr effect in muscle tissue. In highly active tissues, lactic acid is produced. And so lactic acid, being an acid, will actually cause more oxygen to be released from the hemoglobin. And CO2 additionally modulates O2 binding. So oxygen can actually bind to amine groups and form what's known as carbamates on the N terminal of the blood proteins. And so when you form this carbamate, meaning I've got high concentrations of CO2, it reacts with the amines, makes what's called a carbamic acid, and I release more H pluses that cause even more O2 to be released from hemoglobin. So lots of things going on here that cause the oxygen to be released, but essentially this Bohr effect is really important. This was discovered by the dad of the Bohr atom, the person that came up with the Bohr model of the atom. So we got one more molecule that we need to talk about that affects release of oxygen, and that is 2,3-bisphosphoglycerate. And it actually binds to hemoglobin and stabilizes the tense state. So what they found out was highly purified hemoglobin binds oxygen more tightly than hemoglobin in blood. So they figured there was some factor in blood that caused hemoglobin to bind oxygen less tightly or be more willing to give up the oxygen. And they eventually found that molecule, and it was 2,3-bisphosphoglycerate. It's found in mammalian blood, and it decreases hemoglobin's affinity for O2 by stabilizing the T state. So again, if you can stabilize that T state, then the molecule is going to be more likely to give up the oxygen and adopt that T state. And so this BPG is what it's referred to, allows for extra layer of modulation of the hemoglobin oxygen binding under various conditions. And so here is a picture of BPG. It actually binds to the interior. Remember, in the T state, you've got quite a large cavity in that interior, and BPG will bind in there, and you can see that it's got some electrostatic interactions. Remember, when you get to the R state, that internal cavity collapses, and so BPG can't bind as efficiently in the R state. But when you have that cavity, BPG can actually bind in there and help stabilize the T state. Okay, so we're going to bring kind of that BPG and fetal hemoglobin and higher affinity together. So fetal hemoglobin actually has a different subunit composition. It's got 2 alpha subunits and then what are referred to as gamma subunits. And it actually has a much lower affinity for BPG than adult hemoglobin. But fetal hemoglobin binds O2 more tightly than maternal hemoglobin. And the reason that it binds more tightly is kind of like myoglobin. You need to make sure that the equilibrium favors the transfer of oxygen from the maternal hemoglobin to the fetus. If they had equal affinity for it, then you just set up an equilibrium there. But the fetus needs lots of oxygen, and in fact, fetuses have been referred to as parasites. This is kind of an example of that. The fetus needs a higher affinity for oxygen, so it actually pulls that oxygen and favors binding to the fetal hemoglobin. Now, if we move to high altitude, the actual pressure is less, and the pressure of oxygen, or the partial pressure of oxygen, also is reduced. And so that's what we can see down here in this graph. So so in normal atmospheric pressure, we got this red line right here. This is our normal release. But if we changed to a higher altitude, we have less partial pressure of oxygen. Our venous inside us, that partial pressure is not going to change, but the arterial pressure of O2, there's going to be less O2 there. So what you're going to see is we're going to get less fractional binding of O2. But when we get to our venous and we have this normal hemoglobin in there, we're only going to release 0.3 of our oxygen, where at normal sea level, we're releasing 0.38. Now, that is painful. If you've ever gone up to really high elevations and ran or even climbed stairs, you can tell that your body is not getting as much oxygen, so you tend to breathe faster. So one way that you can fix that is you can actually start to produce more BPG. And again, the BPG stabilizes the T state, making it so it has less affinity. And what you do is you get this shift to this red curve there. And so again, it's going to have less affinity. So remember, as we move down towards the bottom right corner, that illustrates less affinity. And now you look at that curve, the venous PO is going to still be the same. The arterial PO at high elevations is still reduced. So the hemoglobin is not binding as much, but what you do is you see a greater release of that O2, so 0.37. So essentially your body's releasing about the same amount. And you can adapt to high altitudes fairly quick by using or creating BPG.